So the goal of this video is to help you finish up the last part of this population genetics and evolution, or the Hardy-Weinberg Rule. So what you should have learned on the Hardy-Weinberg is that there's these 5 qualifications that determine to make sure that a population is in equilibrium, genetic equilibrium. So remember, this is that this p squared plus 2p cubed plus q squared equals 1. And so hopefully the goldfish activity helps you out with that. So you should have a data table completed here, showing the calculations for the genotype frequency. Right. So the frequency of P's, so the frequency of homozygous dominant, homozygous recessive, and heterozygous dominant. You've answered these analysis questions, you read this conclusion. You should have done that all in class. Now, what you need to do is you now need to do the chi-squared calculations. What chi-squared is the goodness of fit test. Essentially what you're looking at is how close to what you expected your data to be is your actual data. Now, sometimes in classes we might do this in the M&M lab. We might actually eventually do that. But what I want you to do is on the goldfish. So if you look at the previous information, there should be about in this ocean, this last, we're going to use this very last one right here, this last generation, generation 5, or the last generation you got to in class. You're going to use that very last one to do the chi-squared. So on that last generation, there should have been 84% of your fish that were gold colored. And what the chi-squared does, this chi-square analysis does, is we're going to look to see, okay, if it's not 84% gold, then what is the reason for that? We're not necessarily what is the reason for that 84%, but is it off enough that we can say, okay, well, if it's very slightly off, if it's instead of 84%, it's 86% or it's 83%, is that due to chance, or is there some other reason? Is it off a great amount to where we're like, oh wait, there must have been some kind of selection going on. There must have been some kind of evolution, some kind of mutation going on that caused that. And so this is what we call, again, this goodness of fit test, or the chi-squared analysis. So when we start, we're going to use a probability table, and we're going to start with the null hypothesis. Now, null hypothesis is not a standard hypothesis. A null hypothesis is essentially saying that if everything is the same, there will be no difference between the treatment and the control. So there will be no difference between what we see and what we expect. So another way of saying that is the hypothesis that is observed pattern data and the expected pattern are effectively the same, different only by chance, not because they're truly different. So the null hypothesis is essentially saying that everything constant, we will see the same results, and any differences in those results is merely due to chance. So the null hypothesis we're going to say, and I'll come back to the rest of this, is right here for this one. So the differences found in the last generation population of the goldfish and the expected population is essentially the same and only different by chance. So again, we're going to expect this 84%, and the chi-squared is going to tell us that if our null hypothesis is correct or not. And our hypothesis is saying that if everything's the same, then there's just a slight difference, then it's completely due to chance. Now, what the null hypothesis is this right here, or the chi-squared, is this formula right here, and I'll write it a little bigger. Chi-squared is equal to the sum, so basically all the observed minus all the expected of the observed minus the expected. So what do we actually see minus what do we expect? So that would be like we saw it was 96% and we expected 86%. We're going to square that and then divide by the expected. We're going to divide by that 86%. And that value will say, okay, this is how far away from where we were supposed to be. So the chi-squared is the difference between the observed and the expected values increase. So the chi-squared value will increase as the expected difference will increase as well. So what you need to do is you need to then look at generation 5, go up, look at generation 5, and fill in this chart. What did you observe? How many browns were there? How many golds were there? Well, what's 86% of the total number of browns you had? What's 86% of the total number of golds? So 86% of 20 total fish is the brown amount, and then the other 14% is the gold amount. So that's what you expected. Okay, so we saw this many brown, we saw this many gold, you'll get a total. Well, then take that total and find 86% of it. Take that total and then find the other 14% or just subtract. So these totals should be the same. And then the difference, observed minus expected. So right here it's observed minus expected. We say, okay, we saw this observed, we subtract that expected, we get that. We saw this observed, we saw that expected, we get this amount. So you just subtract down to get this value right here. And then you go down to the differences squared. So you just take this value and square it. You take this value and square it, and that's the answer. The total here isn't really necessary. You don't worry about that. So right here though, the next one, it's just saying, okay, if you took the observed minus expected, you squared it, what is it, and then divide by the expected. So you take this number and divide it by expected. So you take the number you have right here, difference squared, and divide it by what you had in row 2, the expected. So you get that number there, you get that number there. So then you take the sum of the difference squared, divided by the expectation. So you take the sum here. So you take that number plus that number, and that'll give you your chi-squared. So you say, okay, I got this number, and I got that number, that's my chi-squared. Okay, so I basically just made this chart for you so you could take this formula and break it down into steps. Okay, so now you're going to get a number. And that number could be really, really large, that number could be very, very small. And the larger the number is, the more likely that difference that we're having is due to something other than chance. So again, the difference between that number, the larger it is, the larger chi-squared value, and the larger the chi-squared value, the greater it is due to something other than chance. So right here it says, now you must determine the probability of the difference between the observed and the expected is simply by chance. So we're going to take this chi-squared value, just for sake, let's say that our chi-squared value ended up being 1.62. So we're going to take that, and again we got that by adding together these numbers right here. Okay, so we're going to take the observed minus expected squared divided by expected, observed minus expected squared, and we're going to get these two numbers. So if we add those two together, we get 1.62. So we're going to take that number, and we're going to find what's the degrees of freedom. And I've filled it out right here. Your degrees of freedom is the number of categories you have. So we had two different colors, so there's two different categories, and we're going to start at track type 1. If we're doing colors in M&Ms, there's 5 different colors in M&Ms, and so the degrees of freedom in M&Ms is 5 number of colors minus 1, so the degrees of freedom is 4. But here we only have 1 degree of freedom. And so we're going to look at the degree of freedom, and it talks about standard square deviations for all the classes. But again, the higher the chi-squared value, the more classes that have to be taken into account. So the more classes you have, the more freedom you have to say, okay, well that was due by chance. That's what this is saying. So you then use this chart right here. Now, on this chart, it's supposed to be right there. On this chart, you need to notice this value right here. That value right there, 0.05, anything to the left of it, we're going to accept the null hypothesis. We're going to say that any percentage that we have over here on the far left side is merely due to chance. Any number we come up with that's a chi-squared value that's to the right side is due to something other than chance. So again, anything on the left side, we're going to accept the null hypothesis. We're going to say that anything on the left side, any chi-squared value on the left side is merely due to chance. Any value we get that's on the right side is due to something other than chance, some kind of mutation, selective breeding, something like that. So our 1.62 lands right here. So what that says is that we've got between a 25%, between a 10 to 25% chance that difference between what we saw and what we expected to see was due to merely chance. Okay, so we have a probability of 10 to 25% that the difference was due to chance. Okay, so again, it says right here, so 1.61 would be expected on the 4. It would say that we've got, so 1.61 is right here, and it's saying that this is from the M&Ms, that if the degrees of freedom is 4, it's right here. So this is saying that there's almost a 90% probability that difference, that very small difference we see, is merely due to chance. But if it's something larger, whereas a large number, like if it's 15.09, you have to go all the way over here and say, okay, there's less than a 1% chance. There's a less than a 1% probability that difference between the two is due to just random chance. It's because of something's going on, some mutation, some kind of evolution. And so, again, you notice that it's a 5% difference. And that's where we sit. And so when you do your null hypothesis and you do your chi-squared, this 5%, this 0.05, is essentially the dividing line. And take your paper and mark a huge mark down the middle of that. So you take all that, that's your chi-squared value. So what I want you to do is take that number and then figure out, are you going to reject or accept your hypothesis? And so I want you to do it down here on the bottom and say, I accept my hypothesis. Down here on the bottom, say I accept my hypothesis, and based on this chart down here, because the chi-squared value was less than 0.05, there's a 5% chance, that's the probability that it's due to chance. Or I reject my hypothesis, my null hypothesis, because it was greater than a 5% probability that the differences was due to chance. So again, that's chi-squared. It's a statistical test to determine the difference that you see and what you expect is due to just a random occurrence, or is it due to something that would be mutations. And from that point is then when you do your testing to see, okay, well, what is that mutation if your chi-squared value does come up large.